Hi, welcome to Analysis of Algorithms. We're doing the homeworks for Chapter 1. Okay? As always, you're supposed to do the homeworks first and then check your answers with me. So there's two parts of it. Section 1, Chapter 1, Section 1, Chapter 1, Section 2. Okay? The first part is just getting started, so it's a lot of, easy, non-technical questions. The second part is more technical, and we'll do that on Excel. Okay, so problem 1.1-2. Other than speed, what other measures of efficiency might one use in a real-world setting? Okay, so it seems like in our class we're very much concerned about speed. Oh, can you do this faster? Can you do this better? Etc., etc. But there are other things to be concerned about. So this is 1.1-2. So another thing that was very important years ago is space. Okay, how much memory does it use? Okay, that's a very big thing in the 1970s and 1980s and the 1990s when you don't have so much memory. Nowadays, every single key drive can hold 10 gigs. It's not such a big thing, but at one point that was a very big thing. Other types of things is, let's say you have a computer hooked up to some measuring device, okay? And that measuring device might take time. So question, how many times do you want to have that measuring device do things? Okay, for example, it could be connected to somebody taking their blood pressure or something like that. Well, you don't want to take the blood pressure too often or too frequently or too infrequently. So some type of measuring device, to what extent does your program ask for that measuring device? Okay. A third thing might be you're saving data, let's say in a disk. You want to know how often do you have to move the disk around. In other words, move the head of the disk around. So that's a topic that's a little bit less of concern nowadays, but or how many times you want to move large amounts of data. So memory issues. So those are types of things that we will be interested besides for just speed. Okay, so those are examples. I'm sure you could think of a lot more examples. Okay, next. Again, these are just questions that are here to make sure that you read the book. So let's do 1.1-3. Select a data structure that you have seen previously and discuss its strengths and limitations. So again, not only do they want you to have seen this, read the book, but they want you to have seen it. And again, we assume that you've seen a data structures course. So I'll just pick one. How about just a linked list? Okay, and linked lists have positive things and negative things. We're going to see a lot more about data structures in chapter 10 and 11 and stuff like that. But let's talk about the linked list. The good things, okay, is you don't have to declare how much space you have. Okay, you can always add another element to the linked list. You can always chuck on another one, no problem whatsoever. Okay, so adding elements is a good thing. It's easy. Okay. Also, if you have an array and you take out an element, you lose a customer, so you're going to have a blank space there. You don't have that, so it's easy to delete. With a linked list, it's easy to delete. Okay, why is it bad? Okay, no random access memory. With a linked list, you can't just go to any element whatsoever. You have to traverse the other links, the other elements too. So it's not very good with that. Also, sometimes, well, if a doubly linked list, it's easy to delete, but sometimes it's not so easy to delete. Things like that. What other bad things can we say about a linked list? Well, again, there's different types of linked lists. Again, this is a question more suitable for a data structure class, but we assume you've seen a data structure class. Okay, next question. 1.1-4. So in the book talks about two problems. One is called the shortest path, and the other is called the traveling salesman problem. Okay, in the 4th edition, it's called the traveling salesperson problem because they're gender neutral. Okay, how are the shortest path and the traveling salesman problem given above similar? How are they different? Okay, so they're similar in the following sense. They're both, the input is a bunch of places that you have to go. Okay, a bunch of points on the map if you want. Okay, now for the shortest path, what they want is, they want to know what's the shortest path between any two points. In other words, what is the shortest way of going from any vertex to any other vertex? Okay, that's called the shortest path. So you have a bunch of cities, and you want to be able to answer this question: what is the shortest way to get from any city to any other city? Okay, the traveling salesman problem is similar, and also it's given a bunch of points on a graph. Okay, but here you're not interested in any two paths. You want to make the shortest tour that hits every one of these things in the shortest amount of time. So you want to be able to go to every single city and come back to the original starting place. But you want the shortest possible way of doing that. Okay, so they're similar in that they're both given a bunch of points on a graph. They're similar in that they're a minimization problem. They're different in that the shortest path gives the shortest path between any two points. The traveling salesman problem looks at tours that hit every single thing. Okay. More importantly, and we'll see this much later on, shortest path is a polynomial problem. Traveling salesman problem is an NP-complete problem. It can't be done for a large size input any meaningful way. Okay. Section 1.4-5 says as follows: come up with a real-world problem in which only the best solution will do. Okay, the best meaning we don't take problems. Okay, and then come up with a solution that is approximately the best is good enough. Okay, so something in the best will do is, if you're making medicines and this is just an example, you're making some type of medicines, you have to have the right ingredients such that the mechanism works, etc., etc. Well, you don't want to have faulty medicines. That's not good. You can't just say, oh, the medicine was a little bit good. Sorry, a few percentage of people who took the medicine died. It was an approximate solution. We don't want that. Okay? If you're building a bridge, okay, you don't want to have, you have two sides of a river and you're building a bridge. Okay, if they're 1 inch off, it could be the whole thing. If you're building one this way and one in this way, if they're 1 inch off, you don't want that. Okay, so that's not a good idea. Okay, so it has to be exactly perfect, the best. Okay, approximate algorithms. Okay, and there is a chapter 35, I think, that deals with approximate algorithms. Many NP-complete problems can't be solved in a normal amount of time, but they can be solved if you have an approximate algorithm. So we do a lot of that. So for example, a traveling salesman problem looks for the shortest possible route. Okay? Solving the traveling salesman problem is a very hard problem. However, okay, approximation for a traveling salesman problem is done all the time. We'll talk about it later on, but a school bus. A school bus driver has a certain amount of corners that he has to pick up kids on, okay, and he wants to do it in the shortest amount of time because he wants to go home and he doesn't want to work so hard. But if he doesn't get it in the shortest amount of time, he might have a few extra minutes here and there, and so that won't be terrible. So traveling salesman school bus. Okay, so if the school bus tore, okay, if you're doing a school bus going through and hitting every single corner that you need to hit, but you don't do it in the shortest amount of time, it doesn't really hurt anybody. The kids are in the bus an extra 5 minutes or extra 10 minutes. It doesn't really hurt anybody. Another example where an approximation algorithm would do, okay, this is something with packing. If you have a box, this is a big thing in Amazon, whatever, and you have a bunch of stuff that has to go, you don't necessarily want the bare minimum box that you can fit in everything so that you won't waste time. Even if you do, it doesn't really bother you. So that's why Amazon, whatever, they always send these giant boxes and then they just fill it up with fillers to make sure. So there are approximation algorithms used to solve the packing problem, and they don't care to make those approximation algorithms perfect, because it's a pain in the neck. Because if you have a lot of different size boxes, you have to worry about inventory and things like that. So that's not a major thing. Okay. So again, filling stuff in that is not very important, and you can use an approximation algorithm. Okay. So that is the end of the problems in 1.1-5. Section 1.1. Okay. In section 1.2, there are two problems. And we'll go through it. So we're going to do problem number, I think, 3. I'm sorry, problem number 2 and 3. Okay, but I'm going to do it on Excel, and so you'll see it there. And then there's a problem done at the end of the chapter, which we'll do. So this is problem 1-1. Okay, so that takes care of this video. Hi. So the rest of the problems we're going to do on Excel, and I wanted to do them like this. We'll post it like that. Okay, so let me just read problem 1.2-2. Suppose we are comparing the implementation of insertion sort and merge sort on the same machine. For inputs of size n, insertion sort runs 8n squared steps. That's not really true. It's really closer to n squared, while merge sort is 64 n log n steps. Okay, they're just making up an example. It doesn't matter. But here's the question. For which values of n does insertion sort beat merge sort? So again, insertion sort is an n squared algorithm. Merge sort is an n log n algorithm. So they want to do this. Okay, basically the way that you do this is you set up an Excel sheet. And you put down n over here, 8n squared, 6, that's just English. These top 3 things are simply English. And then you plug in a bunch of values for n. You have no idea what the real answer is, and you plug in the values here. Let me just show you how this works. This is 8 times a2 is that number, and then raised to the second power. You have that. Once you have that, okay, let me just show you what you can do. You just copy that and paste it. You did it once and you get the rest. Okay, same thing here. Okay, this is 64 n log n. Okay, and here's the formula for it. 64 times a2, that's this number, times log of a2. A2 is n. So it's a2 times log of a2, comma 2, that means to the base 2. LG means to the base 2. You do that, and then you copy that. Okay? And if you go down, you'll see for all these values, this insertion sort is 72 operations, and this is 304 operations. So it's better to do insertion sort. This is 648. This is 1825. It's better to do that. Okay, it goes on like that until I put this star over here. Okay, here it's 14,000. Here it's 14,700. Here it's 14,900. Okay, so it's better to do this one, which is insertion sort, than this one. Okay, than this one. However, from here on n, okay, it's better to do merge sort. Okay, so from here on n, it's better to do merge sort. These numbers are smaller than these numbers. These numbers grow much bigger. The main point is a squared algorithm grows much faster than an n log n algorithm, even with this leading exponent. Okay, so from 1 to 43, it pays to do the insertion and not the merge. From 44 and on, it pays to do the merge algorithm and not that. Okay? And it's going to go on forever like that. Okay, I just want to show you one cute trick. Let's say I wanted to know, like, where it changes. You know, we'll do this next time. We'll do this in the next problem. Okay, here's another one. Okay, so let's do this. 1.2-3, what is the smallest value of n such that an algorithm whose running time is 100n squared runs faster than an algorithm whose running time is 2 to the n? So again, we do the same thing. 1 like that. Here's n, we plug in n. Here's 100n squared, that's in English. Here's 2 to the n. Okay, and then we simply plug in the numbers. Look at that. That's 100 times a squared. A squared is this times that times to the second power, and this is 2 raised to the second power. Okay, and you get that. Okay, it turns out that the answer is, okay, again, this is a number, this is a squared algorithm, this is an exponential algorithm, this is a squared algorithm with a large leading coefficient. So these numbers are big in the beginning. However, eventually exponentiation grows much faster than squared. And that point is between 15 is at point 16. Okay, just want to show you one cute little trick. Let's say I wanted to know clearer, where is the cutoff point between 15 and 16? So watch what I can do. Watch this. Let's do this. 15.0. Nope, that's not a good thing. 15.0. I know what that is. 15 point. I know what that point is. I see. Hold on. Okay, now hold it. 15 point. Oops. Let's erase everything. Sorry for the delay. Okay, ready? 15.0. Enter. Okay. Let's do the 15.1. Enter. 15.2. Okay, now watch this. Okay, so I have a nice sequence going on there. And let's change it. Now I've gone, instead of going 1, 2, 3, 4, 5, etc., etc., I've gone from 15 to 17.4, but in increments of 0.1. And Excel figured out my pattern here. I did 15.0, 15.1, 15.2, and it figured out the pattern. So now let's see where this cutoff, this trade-off is. At 15, this is 22,000, this is 32,000. Oh, so it's already bigger. Okay. So I am wrong. So let's try this from 14. Sorry, 14.0. 14.1. 14.2. Okay, let's copy this. Okay, let's continue the pattern. And automatically this is all adjusted. Let's see, this is 18,000, this is 20,000. This is 20,000, this is 20,400. This is 21, this is 20. Okay, so right here, Here's where this number is bigger than this number. So that's the cutoff point. So the real cutoff point is 14.4. Anyways, that's a nice problem. Okay, great. Let's do the last problem from chapter 5. Okay. This is problem 1-1. It's on page 14 of the 3rd edition. I don't know what page it's on the 4th edition. For each function f of n and time t in the following table, determine the largest size n of a problem that can be solved in time t, assuming that the algorithm to solve the problem takes f of n microseconds. Okay, so I just like to show you how I did it. It's not hard. Okay, so I put down at the top of what they have. Okay, time, 1 second, 1 minute, 1 hour, 1 day, 1 month, 1 year, 1 century. That's all English. Okay, but we want to know these things in terms of seconds. Okay, how much seconds it is. So 1 second is 1 second. 60 seconds is 60 seconds. 1 minute is 60 seconds. An hour is, this is how many minutes you have, and I multiplied it by 60. So an hour is 60 minutes. Each one of them is 60 seconds, so that's 3,600. A day is this many seconds in an hour times 24, so we get that. A month is this many in a day times 30, so we get that. Okay, a year is, this is how much in a day. I could have done multiplied by 12, but that doesn't matter. This is how much in a day. A year is that times 365.25, whatever, we're not interested in that. A century is this many times 100. So the amount of seconds in a year times 100 is the amount of seconds in a century. Now, each second, the computer can do 1,000,000 operations. So I just take this and look at this formula. It's B2 times 1,000,000, okay? And then what I simply did was I copy this and then I paste it here, okay? And it tells me 60 seconds, how is 60 million operations, etc., etc. Okay, great. So that takes care of the number of operations. Now, for this, it's a little bit more complicated. And these numbers were too big and I couldn't deal with them. My Excel couldn't deal with them. I'm sure there's a way of doing it. Okay, but basically what you have is here. You want the square root of n is equal to 1,000,000. Tell me what n is. Okay, well, it's very easy to do that because this, you know how to invert the function of square root. Okay, you have square root of n is one function. Okay, the inverse of that is going to be what? It's going to be n squared. Okay, so basically what I did is I took these numbers and I squared them. So b to the third, that's this number, to the second power. Okay, so all these operations, what I did was I inverted them to find the solution. When is it, you have square root of n, square root of n is equal to num of ops. Okay, it's in English, whatever, forget about that. Num of ops, square root of n is equal to that. So you solve for n, and you solve for n by having the inverse. So we did a lot of this in homework number 0. Okay, okay. N is just that. That's the number of operations. You don't have to solve for n. N squared, here I had to take the square root. So I took square root of B3. I took this number, I took the square root of it. That's going to give me the thing here. Okay, same thing here. Just I did it for the first one and then I copied for all the rest and I got the answers. By the way, you have the answers on a piece of paper. N to the third, what is the inverse operation of n to the third? Raise it to the cube root. The cube root of n to the third is n, so we get that. Okay, and 2 to the n, the inverse operation of that is log base 2 of n. So that takes care of that. Okay, there are two things I cannot do. I don't know how to do it. And one is n log n. I don't know how to solve for n. If I say n log n is some number, solve for n, I don't know how to do it. Another thing is I don't know how to solve for n. If I say n log n is equal to x, solve for n, I can't do that. I just don't know how to do it. I'm sure there is a way of doing it. You probably have to test a lot of values and things like that. Anyways, that takes care of that. Okay, so that's the homework for chapter 1.